All right, so I'm not going to get started just yet, but I want to make sure that everything is working and so on. So, if someone could write something, if they can hear me, that would be good. I know there's a bit of a delay, so uh, it'll probably have to be written in just a moment. All right, great. So probably just going to wait a few minutes just because this is on the schedule for 8, and so or 8 in Eastern time, so might as well wait till then. All right, so it is 8 in my time zone, so should get started here. So okay, so the general idea here is well, okay. So actually, maybe a bit of background first. So in the movie that many of you and probably a lot of you have seen at this point, given that you're in this stream, in the movie Arrival, the science fiction movie that just came out recently. The background screens, or a lot of the background screens, have Wolfram language code on them. So uh, there's a maybe more complicated story about exactly how that came about and so on, which I think someone usefully put a link to a blog about how that happened at the top of the chat. Um, so you can look at that if you're interested. But otherwise, so I primarily wrote the code that ended up being on a bunch of the screens, and so I guess I'm just going to go through a bunch of the notebooks and a bunch of the code that was made for that, and then we have the data, so we can then maybe try and see if we can do a bit more. So all right, so let's get started. So essentially, um, what we had to work with was we were given from the production company these a bunch of these the so-called logograms, which are the alien language. So I'm going to assume a little bit that people have seen the movie, but essentially in the movie there are these aliens, and the movie's about trying to communicate with these aliens and so on. And the aliens have this writing that looks kind of like this. Um, and so these characters, I believe in the final movie, uh, they don't actually refer to them with this term, but they called them logograms during the production and so on. And I think in this short story that it was based on, they were called logograms. Actually, I'm just going to. I want to check again if people can hear me, because I have everything open on a separate computer, and I'm looking over at it and it looks frozen. So I just want to make sure that everything. Oh no, okay, I just reloaded the page and it seems to be. Yeah, it seems to be working. Okay, never mind. Um, so okay, right. So essentially, the idea here was, so as a lot of you probably also know, most movies, the code that shows up on screens and so on in most movies is usually very inaccurate, or it's either irrelevant or not real, or there are many different ways it can be silly. But basically, as far as I know, there aren't really any serious kind of mainstream movies that have actually bothered to have actual code in them that's relevant and so on. So this was sort of an attempt to have actual code in a real movie. So that's kind of neat. So in any case, though, so from the production company, we got these logograms, which were supposedly, or at the time, they were all the logograms that were going to appear in the movie. So here's the list. So let's see. Let's see how many of these are there. So there are 38 logograms that we had at this point. I don't know if maybe more ended up being made later, but this is what we sort of had to work with. And with each of these, there was generally, if I remember right, a lot of these had kind of translations that were attached to them when they were made. So, like if I remember right, this one I think might be the symbol for either one of the main characters or maybe one of the aliens or something like that, and so on. And then if they wanted to for instance, have say something about that character or that alien or whatever, they would combine this symbol with another symbol and maybe make something like this, where you can see this part's the same, but it's got this added part here. And so this was sort of the main way that I think these were made. So essentially though, so some of these we had a sort of a vague sense of like what they were, quote, supposed to mean, but there was no, as far as I know, there was no real actual completely systematized way these were made. There were a few kind of conventions that were used, but for the most part it was just, they were just made in presumably Photoshop or something like that. In any case though, so let's see. So let's try and do something with them. So one of the first things that they looked at, so in the movie, one of the things is that the aliens, there's all sorts of stuff about the aliens and the number 7, and in particular they have, the aliens are these heptapods, and so they have, these like 7-fingered, they have 7 arms, and then on the arms they have these kind of 7-fingered hands, and so on. And there were all sorts of, in the original script, the 7 was like a kind of a thing that there was all this 7-fold symmetry and so on with the aliens. Now later on, I forget why, but that they were still heptapods, but then a bunch of things were changed to 12 and so on. And so in the end, we ended up looking at these as maybe having some sort of 12-fold symmetry. So again, the idea here was to try and look at these as if maybe you were a character in the movie, and what would you actually do? So given that you have these aliens and they supposedly have all sorts of 12-fold symmetry and so on, maybe and it appears that the logograms have these different sections, then maybe you can break them up into these different sections and so on. So that was the first thing to try, and so that's what this is here. So essentially, this is just some function that's probably not particularly well written. It's been a while since I've gotten to look at these, but right. So essentially, this is just pulling out the different sections. So you can say break logogram and then give it some logogram. So for example, I have this one I here, which is just some generic logogram. So I can say something like I and then break into 12 sections, and then that has each of them like just that section, but within the frame of the original logogram. So we can crop all of those with image crop, and then we get these nice things here. So we could try just cropping, let's say the first logogram, and okay, there it is, or maybe the 5th logogram, and right, and so then these are all the supposed sections. Now, okay, that's fine, I guess, although it doesn't seem like it's immediately super useful. So the next thing was just to kind of look at, okay, well, just as a human, is it easy to tell if there's any sense in these sections? Like if you actually break it up into these sections, does that seem to be sensible? And so you can just sort of visualize how some of them are cut up, and here actually, so what this is doing, this is actually, I'm only going to do this for a few of them. So right now that was trying to compute. I was trying to break up the sections on all 32 of the logograms. I'm just going to do 10 of them for now because I know it'll take it maybe 30 seconds or so to run it for all of them. So So yeah, so let's see. So we can try. It's okay. We can just visualize them and see them next to each other. Okay, that's okay. Now we can also, and so essentially, actually, what this is, each column is. Let me see if I can get this right. Right. So each row is a logogram, and each column is that particular section of that logogram. So for instance, the left column is all this like bottom right looking section of all the logograms and so on. And so you can see some similarities and so on. So for instance, between these logograms, they have differences in other columns like here, but right in this section they're exactly the same. And same with this section, this section, this section. And so you can start to see a bit about them. And we can keep going and so on, and we can do some things that maybe make this a bit more pleasant. So this, for instance, just orients them all. So regardless of which part of the logogram it came from, they'll always be oriented in the same direction. And so maybe you know if this was the same as this here, which it doesn't appear to be, but if it were, then you might be able to compare them more easily and so on. In any case, though, so okay, so we can just this is just nice for kind of visualizing them a bit. And you know, and of course, again, if this were a real situation, and this is what we were actually doing, we're trying to understand this language and so on, that would probably be a somewhat useful thing to be doing. So okay, so that's maybe the first thing. So they're on the order of 8 different files here, and as well as some other stuff. So I'm going to kind of keep moving through this because again, at the end, I want to be able to play around a bit with these and do some new stuff. So okay, so let's see. So we can maybe try. Let's look at. I don't know. We can look at this one. I don't know what's in. It's been a while since I've looked at these, so some of these are a surprise, and a lot of these, I should say, also go nowhere. Which at some level is also realistic though, because there are lots of things you try that wouldn't work. So this was just trying to do. Let's see, what is this trying to do? So this is just trying to do various it's just trying to do various like morphological transformations on the thing and see if anything interesting shows up. So this is just doing a skeleton transform, and nothing immediately appears to be happening there. So it doesn't really tell you much. This is just looking at it's just pulling out corners, which is not particularly interesting. This is just trying to pull out corners and then draw lines between them. Maybe see if you can maybe see if there are more corners in certain places, if certain parts are spikier than other places, and so on. And so, I mean, you can see a bit. You can see like, okay, this area is kind of spiky, and this area isn't as spiky, and so on. But again, it's hard to tell immediately what you can tell from that. We got some things. This is applying a kind of random convolution to it. This is getting the gradient, and so on and so on. So you can do all sorts of filtering and so on. And that seems to be most of what's going on here. Now, yeah. So this was not a particularly fruitful file, it seems, but it's a thing that you try, so it's nice to make. So let's see. Let's keep going a bit. Let's how about let's see. Okay, we can go to this here. So okay. So this is again just trying to look at various parts, and this was okay. There, it's slowing down because there are some things that these dynamics are using that weren't or I didn't set save definitions, and so when the kernel, because it's a newer kernel than when the file was made, it'll need to have recomputed that stuff. But okay, so okay, this is just sort of, again, just trying to visualize them in a probably not terribly useful way. So yeah, okay, let's see. I'm going to get to something more interesting. There are some of these that did some more interesting stuff. Okay, so here's one that there might be some more in here. I'm not sure. So what this was doing, right? So what this was doing is it was trying to kind of unwrap them, quotes. So the point being that right, the logograms, I mean, they look like this, and so the idea is just to try and linearize them in some way, which, for those who've seen the movie, without trying to spoil anything, part of the language has to do, or part of the maybe the symbolism or something of the language has to do with the fact that it's drawn as a circle. So it's in the world of the movie, it probably wouldn't really be very useful to linearize to draw them in lines like this, but it's still just a useful thing to look at. So so you can see this here. It's just trying to draw them as lines. Now, actually, okay, there's a thing here. I tried to. I'm remembering when I first did this. So the first thing I tried was trying to just use image transformation, but I was having some trouble doing that because there are different coordinate spaces and so on, and it was unclear if I wanted an image forward transfer and so on. So I ended up just doing this thing, which is a bit of a hack, but it works fairly well. And so all this was doing is it's basically, let's see, right. So it's basically rotating the image and then taking a slice from the middle of it, and then it's assembling those. So essentially what it's doing is, let's see if I can apply this. So let's say 600, and, right, so if I run that, what this is doing is it's basically rotating the image. Actually, I should do it less than 600 times. Let's do it just like 15 times. So essentially what it's doing is it's just rotating the image 15 times, and then it's rotating the image 15 times, and then at each of those rotations, it's taking this slice. It's taking this slice of a part of them. So here are all the rotated images, and so you can see it's just slowly rotating, and so it's taking a slice. It's cutting off half of it, so it's just taking off, I think it's the right half, and then it's just finding it's getting all the pixels within the middle row, and then it's doing that for a bunch of different angles, and then it's squishing those all together into an image, and you get something like this. And so you can see them drawn in this nice way, and so on. So okay, so that's fine. Let's see. I want to get to something more exciting. I mean, we may have to just get into trying to write some new stuff, but let's see what else is here. So these, okay, right. So okay, so one thing that was kind of interesting was let's see if I can get this up. Okay, right. So one thing, I believe actually some of this changed by the. Actually, no, I think these were the final. Well, actually, okay, I think these were the final things, but I'm not sure. So essentially, this list here was the list of positions where the aliens supposedly landed, right? So again, for those who haven't seen the movie, the aliens landed in these different places, and I think originally it was 7 places, but now now it's 12 places, and so these are the coordinates of the 12 places where they supposedly landed. And so one of the things was just to look and see if there was some just to try and see if there was some nice pattern for where they landed and so on. And so because, well, right. So one of the things here, so one of the concepts was well, it could be the case that maybe they may have right. Well, it may have been that they landed maybe in some particular map projection, right? Maybe in some map projection that the aliens used or something. They maybe landed in some very orderly way, but that just using for example, this looks like, I think this is an equirectangular projection. It's not obvious what the pattern is, and so the idea was to try and see with a bunch of different projections, where does it look like they are. And so let's see if we can. Yeah, so here, using there's a function in the Wolfram language called geoprojection data that let's see if we can see it. So essentially, right. So this is getting some subset of it, right? So this was getting all the projections that apply to the whole Earth, because I believe there's some projections that only apply to, that are kind of projections only for certain hemispheres and so on. And so, okay, right, so we're using this list of projections, and so let's see how many projections is that. Okay, so we had 111 projections, and the idea was just to, take these maps, which are just random ways of just visualizing the things, and show them in all these different projections. And so what this is doing, I mean, just to sort of show off some of the geodesy stuff and so on, what this is doing, I mean, it's showing a bunch of this is showing the different landing sites, and then it's got lines from each site to its 3 nearest neighbors, and then it's got a disk around that site that is 1,000 miles. It has a radius of 1,000 miles. And you can see, of course, that the disks and so on are all distorted properly for that projection and everything like that. So, so let's see, though. So from this was generated, let's see if we can see it in a reasonable way. Yeah, so okay, so here was, let's see what the other one was. I don't know what the difference between these files is. Oh, that's just an older version. Okay, well, in any case, the idea here was to just try and show it in all these different projections. And so this has just got a list of, I mean, this is basically just renderings of this map in all sorts of different projections, or I guess in all 111 of these projections, I think. So yeah, so we can take a look at some of these, and you can see there's some nice funky projections. It's also just fun to look at all the different map projections, but yeah, you can see, okay, that's a good one there. There aren't. This is a good one, the Cassini projection. You can see that there aren't many, I guess, obvious patterns for these in any of these projections, which again isn't necessarily surprising to us because we know that these positions were probably not picked. That whoever chose these locations probably didn't have a an Euler map or an Euler projection map sitting in front of them. So it's maybe not super surprising, but you wouldn't necessarily know that if this was a real situation. So okay, so let's see. So let's try and do some new stuff here. Let's just make a new notebook. All right, and I'm gonna make the text a bit bigger. So if anyone is having trouble reading the text, just let me know, and I can make it bigger. So okay, so let's see what we can do. So we have our logograms. Now one thing that's kind of apparent is just that a lot of these logograms share large sections. So a lot of them are very similar, plus or minus little bits. So for example, you can see these ones look like they're basically the same, except that this one has this little stuff up here and it's got this hook on the inside here. Actually, if I remember right, that hook was one of the only things that had a well-defined meaning, and I believe that hook was supposed to mean that it was a question. But all right, so we can try and see though, maybe which. Well, first of all, let's say we have these two and we just want to see their differences, so we can do that pretty easily. So we can get the first two of these, and then I think we can just say image difference, and that's probably all we need. Oh, whoops. Okay, we actually need to apply image difference because it takes a list. Right, so okay, so that's the difference between those. So if I say image difference of, whoops, okay. So if I say image difference between that and that, apparently that's it. So that is right, so that's kind of cool. So now let's try saying color negate. Okay, so that's kind of the logogram difference between this and this. So if I take this logogram here, actually, I'm curious. So this is actually the difference and not just the subtraction, so it might not necessarily work. But if I say image add of that, comma that, oh, that's not quite useful. Maybe I need to, that's not very useful either. Okay, hold on. Oh, actually, I know what the problem is. The problem is that we're adding two things where we're trying to add the black parts. There we go. But basically, image add is adding together the values, and white is a higher value, and so because they're just grayscale, and so you have to color negate them on either end. But okay, so yeah, so you can see that this is basically, this thing here is basically the logogram difference between these two here. So that's kind of neat. So okay, if we're kind of staying in character, that's probably an interesting thing to be able to get. because it seems like basically this character is a mixture of this character and then this, whatever this is here. Let me see. Let me just save this. Okay. Whoops. Okay. Whatever. Well. So. All right. So that seems nice, and we can maybe try this for a few other examples. So instead of just 1 and 2, maybe what's another good set of them? So we can maybe say 1, 2, 3, 4, 5, 6, 7, and 8. Let's try 7 and 8. Okay, yeah, those ones look good. So what's the difference between 7 and 8? Let's see it. Oh, that's a mess. Okay, so it seems right. So those have got a messy difference. Actually, that's interesting. I assume that's because they're not perfectly lined up or something like that. So we can maybe see. Let's see. Maybe can we do that? Yeah. Okay. So that's showing them both on top of each other. But that's thinking what a good way of showing those might be. Oh, we can show edge detect maybe applied to both of them. So we can run. Let's see if that's a useful thing. So we can run edge detect on both of those, and then we can maybe look at the edges just so that we can compare them and see if the edges are kind of match up or not. So here it looks like the edges do match up. So I don't know why the difference is. I mean, again, I guess that they must not be perfectly lined up in some way, and so their differences has got all this stuff around it. But which is to contrast this one where the difference is this beautiful thing. But okay, we can maybe later we can try and write something that will line them up perfectly, because it's also presumably the case that if these were actually being collected from the aliens and so on, you'd probably have to do a bit of work to get them to line up, because they probably you wouldn't be able to capture them and so on, and the aliens wouldn't draw them so that they're perfectly always oriented in exactly the same way and everything. So presumably that's something you'd need to do anyway. But okay, let's play around a bit more though. So okay, so it seems that it is useful probably to get the differences here, because there are bits that can be extracted. Let's maybe look at, I don't know. Well, we can try and again this little hook here appears in a bunch of places. So we can maybe try and find another case where the hook appears, and then okay, these two look good. So we can get that one, and we can get that one. There we go. So we maybe say image difference of those two. Okay, that's a nicer picture, although that's got more on it than just the hook. But okay, but we can see again. Okay, so we got the hook, and then we've got all the other bits that are not shared between these, because I guess they do have some other differences and so on. But okay, so that's good. Actually, I'm curious. I don't know if image difference cares about. I'm pretty sure image difference does not care about if its inputs are both color negated, for instance. No, it doesn't care. Okay, because image difference. Let's see how image difference is defined. Right, so it effectively finds the XOR of the pixel values for binary images, but it's right. It'll do the grayscale equivalent if the images are grayscale, presumably. So right, so then that works, because it won't care if both the images have a pixel of 1, it's the same as if both the images have a pixel of 0. It's the same output. But okay, so okay, that's nice. If I do that, then it will be very broken. Okay. Well, let's see. Okay, let's delete that. So one thing we could try and do is we can try and just automatically maybe compare these in various ways and see which are the closest. Yeah, actually, let's do that. So one thing we can try and do is just try and find which images, because right now we've just been manually pulling these out and saying these two look very similar, except for this little piece here. But we can maybe just try and pull out. We can try and kind of automatically try and find those. So one thing we could try and do, we can just make a nearest function on these. So I believe I can just say something like that. So I2 again is the list of our images, and nearest, that'll just make this nearest function here. And so now if I say, well actually, okay, I don't know what it's doing. it's saying input dimension 100, but I'm not sure what that means. So, because the thing is, when you give nearest an image, it can nearest, depending on what you give it, because it can often, usually with nearest, the simplest case is you give nearest a bunch of vectors, and then it will find the distance in Euclidean space and so on. Except you can use different distance functions, and of course, if you give it something like an image, you can't really find Euclidean distance, at least not directly. And so you can use different distance measures. And so I don't know what it uses by default for image distance, because I know in the past it's used various things like image distance, which I believe defaults to something like the number of the average pixel value of the image difference. So basically the average pixel value of something like this. But I know for then there would be more than 100 dimensions in the input. And on top of that, also I know that for things like classify, classify has automatic feature extraction. So it'll extract a feature vector from or you can tell it to use a feature extractor. So it'll extract a feature vector from your image, and it will then use that to find the differences between them. So actually, you know what? We'll come back to this in a second, because I had another idea that I don't want to forget, which is which might be kind of cool. So one of the things you can do. So actually, I'm not sure what version this is or will be out in. So this is, we're running here a version of the Wolfram language that doesn't entirely exist quite yet. And so I'm not entirely sure if some of the functions I'm about to use, quotes, exist. And by that I mean that you can use them. But I think that this would be a cool thing to try. So one thing that we can try and do. So there's a function at least in version 11.1, called feature extraction. Okay, it says it's new in 11. Let's see. Okay, no, this is released. So right, a version of this function is released. So what we can say, right, so feature extraction. So you can just give it a bunch of examples, and then it will generate a feature extractor function trained from the examples given. And then you can also give it an extractor, which gives the feature extractor method. And here are a bunch of the built-in methods, and so one of them is image features, which gets a semantic vector from an image, is what it says. So okay, so let's see. I'm just looking down this list here. Okay, right. So let's see. So what we can do. So the idea here is what if we want to kind of, quotes, semantically compare some of these logograms. So by that, I just mean that we have these different logograms. We don't necessarily want to compare their actual pixel values, but we might want to compare them in some kind of try and, quote, semantically compare them. And by that, I just mean compare, this one kind of looks like that one, but they're not necessarily sharing pixel values. Maybe one of them is kind of rotated, who knows. So we can try just using feature extraction to represent that. So first, we can try just doing this. Right, so let's just run that. So I'm just going to train a feature extraction function, just like that. Okay, so it seems that, so here I'm just using the default extractor, which I don't know what it chose to do. It presumably has some algorithm where it'll choose what's the best extractor to use, but we can maybe try, because again, there is that one extractor, the image features, which might be really relevant. It may have used that by default or not, who knows, but we can try that in a minute anyway. But okay, so we have this feature extraction function. So now what we can do, given that we have, for example, this logogram, we can apply this feature extraction function to this logogram, and it will give us a vector, a 37-dimensional vector, I guess. And in theory, this vector kind of encodes, quotes, the essence of the logogram, whatever that might mean. So in theory, this vector will tell us something about the logogram. So one thing we can do, and actually, okay, so right, one thing we can do, and I think there's an example in feature extraction that shows this, but I know that there was also a function in, I believe, 11.1, so that's not released just yet, I don't think, that does this automatically, or that just does all this. But there's an example somewhere in here where you can, let's see, it might be under dimension reduction, where you can visualize the things in a nice way. No, this isn't what I want. Let's see. I know that this function exists I know that this example exists because I've used it a few times. We could always just write it ourselves, but it might be just easier to use the example. Well, okay, I guess we can start to write it ourselves. So we'll say, let's say feature vectors. So we'll say, we'll call it feature vectors, and that would just be all the vectors for all of our logograms. Right, now actually I'm thinking about the best way to, okay, so if I do that, if I just run that, we'll end up with this here. So we'll end up with this two-dimensional thing here. Now, one of the things that we can do is we can run dimension reduction on it. So we can run dimension reduce of this, comma 2. So what does that do? So basically, dimension reduce is a function which, like feature extractor, uses some, or might, depending on what exactly it decides to do, might decide to use some sort of machine learning and so on to essentially try and represent these 37-dimensional vectors as two-dimensional vectors. So it seems kind of obvious that we are destroying a ton of information when we do that. But just for the purposes of visualization, we can maybe try and see if there's some obvious patterns. So we can try, okay, we got dimension reduced there. We can maybe say list plot of that, right? So the nice thing about that is that once you've got them in 2D, then you can visualize them in all sorts of different ways. And let's make sure that we set the plot range to all so we get to see everything. Okay, that's fine. Let's see, actually, I know that you get very different answers when you play around with different methods for dimension reduce. I know in particular I've had good success with this method, which is very random. But okay, let's see. These dots aren't very useful. Let's get it so that instead of a dot, I want to see a logogram there, so that we can actually see if similar ones are near each other and so on. So let's see, what's the easiest way to do that? There are a number of ways we can do that. I believe that we can use plot markers actually. So if I say plot markers goes to none, that's interesting. Okay, how does plot markers work? Let's find out. Well, okay, so it looks like we have, I'm pretty sure the way plot markers works, okay, so, right, okay, so none, I don't know why there's still markers after I set plot markers to none, but it seems that we can give it a list of graphics or something, and it will do that. So let's say plot markers is, if I set it to I2, they'll all be huge, right? But now what I can do is I can do show of hash, comma, let's say image size goes to 50 applied over I2. So essentially what that's doing is it's just showing each of the members of I2 much smaller. Let's maybe make it even smaller, and actually I think that something is slightly wrong here because these all look like the same logogram. Now another thing we can do is that before we fix that problem, you can see where they overlap. There's this, the white parts are overlapping too. So one of the things that we can do is, given that we have some logogram, there's a function called set alpha channel. And so we want to set the alpha channel for this thing to, I believe, the inverse of itself, right? Because we want the alpha channel of this to be, actually I'm not sure if the one argument form set alpha channel might just already do this. I'm not sure. No, okay, it doesn't. So it's basically what set alpha channel will do is it'll set, and let's just go to the documentation to make sure we get the arguments in the right order. Right, okay. So that does the wrong thing. That does not do what we want it to. So essentially what we can do, we want this case here. So essentially it'll set the alpha channel of the first image to the second image, where white means that it's very opaque and black means it's very transparent. So essentially, we want the alpha channel of this image to be like the inverse of itself, right? So we want this to be the image's alpha channel. So okay, so that should be it. So we can now we should be able to just throw that in here and then replace the eyes with hash. Okay, great. So now those have proper alpha channels, but again, there's some sort of problem because these are all the same logogram, just repeated a bunch of times. So let's look at plot markers. Okay, maybe image marker. No, that's something totally different. Okay, let's look at list. Let's look at the documentation for list plot and see if we can find something relevant. Okay, so we've got plot markers. So plot markers, none. So normally use different sets. Okay, plot markers automatic. Do shapes to represent. Okay. Oh, I see what it's doing. Yes. Right. So essentially, the way plot markers works here is each plot marker, right? So list plot can show, so right, so this is just showing a single plot, so this is showing a plot of a bunch of primes, but list plot can take multiple inputs, so I could say then maybe Fibonacci, right, so there's primes in blue, there's Fibonacci in orange, right, and so essentially plot markers, when you give it a list of things, it's not setting the marker for each dot, it's setting the marker for each plot, and so essentially here everything is in one giant plot. But we can easily change that just by applying list around it. So right now we have, these are the points, right? And so it just thinks of these as that's one point, that's the next point, and so on. So it's a bunch of, it's just one plot. But if we apply an extra list around all of these, then there's no ambiguity, and it's then they're all their own plots. There we go. Okay, so those are all the logograms. So let's see if this is kind of at all sensible. Well, it actually doesn't look totally. Actually, it's not that bad yet. Okay, so let's see. So first of all, a lot of the ones that are just kind of rings are over here, while a lot of the more complicated ones are over here, which seems sensible. We can also see that a lot of them that are very similar are near each other. So for example, these two. Let's see if I can zoom in here. I don't know if that's actually zooming in on the stream, but I know on my computer I just use some gesture to zoom in a bit. But you can see these two here look very similar except for the bottom right here, and so it put them very close together. So that seems like a good sign. And I don't know, there may be some others like that we can see that are close together and that are very similar. But okay, so this is actually not looking too bad. The other thing we could maybe do, we can use another function which I'm not sure. I'm gonna check if it's in a released version. Oh no, that's in 10.4. Okay, this is out for ages. So this is right. So essentially, what this function does, this function lets you generate these kind of clustering trees. So we can see we can maybe. Right, so the point is that this graph back here, we have to use all sorts of dimension reduction to make that graph. And so if we don't use dimension reduction, there's a lot more information there. And so we can maybe use something like a clustering tree to not just burn that information, so to speak, but to actually use it in some sort of useful way. So we can, let's see. So yeah, we can try just running something like this. So I believe we can say, right, so represents element arrow value. So right, so we can just say clustering tree of our feature vectors, and then arrow, I believe, just our images. And we can maybe use our images that have been resized and all that stuff from over there. So, okay, let's see. Let's maybe make them a bit small. Actually, you know what? It might automatically size the images. I know that this function does some stuff. Nope, it definitely does not. Okay, let's not do that then. Well, okay. So I'm just looking at the options to see if there's a nice way to get the images to format slightly nicer, but I guess not immediately. So let's make them a bit smaller. Okay, now another thing we can do is I know that clustering tree has some different, I believe it's called the cluster dissimilarity function. Yeah, there it is. And you can set that to different things, and you do get very different results. So let's try just setting the cluster dissimilarity function to, let's say, complete. There we go. Okay, so that's just, let's maybe make them a bit bigger. Okay, so that's a tree. Let's see if it's sensible. So it should be the case that things that are very close on the tree are very similar, and things that are far on the tree are more distant. So let's try. So we can look at maybe this down here. Okay, so that doesn't look immediately bad. I mean, they've got similar things where there's kind of a blob up there and a blob down there, and that seems to be consistent. We can maybe those ones there don't look super similar, so that's not the best. But we can say let's see. Okay, those ones actually look identical, but they look at least, actually no, they're not quite identical, because this one's got some sort of, this thing's got something going on here that this one doesn't have, but they're very similar, and so you can see it grouped them together. Yeah, it's also got something there, and so okay, so that seems right, and these have been grouped together, and so on. So okay, so this isn't totally silly, and so okay, so we've got kind of this hierarchy of them, and again we can try using a different cluster dissimilarity function. We'll get a somewhat different tree of these things, which again the cluster dissimilarity function just mostly has to do with the precise layout of the tree, but it can still have a bit of an effect on what we're seeing. So, but okay, again you can see though that, you can see that you know these two look similar, and so they're placed near each other, and so that's probably a good thing. So okay though, so that's nice. So all right, so so we've got this kind of taxonomy. So this is potentially, again, if we're pretending that we're kind of in the movie here, you know, we can imagine this would be useful, because you know you want to try and see, okay, well, given this symbol, if we sort of have an idea about what this symbol might mean, what are kind of the related symbols and so on, and we can maybe try and do something useful with that. But okay, let's see. We got slightly sidetracked with this feature extraction stuff. So we can maybe try and look a bit at what we were originally doing. Right. So the original thing we were doing is we were trying to make a nearest function. So what we were trying to do is we were trying to essentially find these. And I'm just trying to. Okay, there we go. Right. So essentially, what we were trying to do was we were trying to find those very similar logograms, because some of them, when you take the image difference, like these two, the only difference is this bit here, and when you take the image difference, you get something like this. And so we want to be able to find all the logograms that are so similar. And so, okay, so this clustering tree scheme might not be so bad, because we can find, for instance, this is again using feature vectors and not the actual logograms, but given the feature vectors, it seems that we can find things that are, it seems that we can do a decent job of finding similar logograms. But with nearest, we might be able to do something that's more mechanical. So again, this is theoretically, the feature extraction here, for instance, might be using all sorts of machine learning and so on. It's generating this feature vector, and we might not need to do that. We might just want to see which are the closest by image difference, and that's a bit easier. So we can come back to this if we need to, but for now we don't need to do that. So again, so now nearest, I don't know why it's saying, again, input dimension 100. Again, that tells me that it might have done feature extraction of some kind, which I think it might do in newer versions. But we can certainly set the distance function to image distance, and then it should be forced to do what we say. So we can say distance function goes to, whoops, it's not in quotes, it's just a function, image distance. Okay, and that just says it's an image. Actually, what did it say before? Input. Okay, I don't know how that works. But in any case, so right, so now the distance function is set to image distance. Now actually, let's just check how image distance works. So it returns the distance between the overlapping regions. Okay, so if they're the same size, that shouldn't be a problem. Okay, they should have the same number of channels and so on, or at least it'll use the channels that they share. Okay, so here are the distance functions. So you've got mean Euclidean distance. Okay, so these are things like, right. So this isn't too bad. We might just write our own thing that just gets basically the number of how many pixels are there in the image difference. Right, so it's essentially how many pixels are different between these two images. But first, okay, we can try this at first. So if we take, for example, our first one. So again, so we know that this logogram looks quite a lot like this logogram here, with the exception just of this bottom area there. So we can try just feeding this one to the nearest function and see if it gives us, well, presumably it'll give us itself, right, because it's in the data set. We can say get us the 2 nearest, and there we go. Okay, so when we asked for the 2 nearest, it gave us the original one, and then it gave us the next one. So we'll let's say get the 5 nearest or something like that. Okay, so they're the 5. Okay, so that's not bad. These ones look very random, but these 3 are sensible. But just as a random point, I know that this one here, for some reason, whoever made this decided to write "Where is Abbott," which is the name of one of the aliens on this image here. And for some reason, I don't know why, because I think that was supposed to be the translation of this logogram, but I think this is the only logogram where the translation is written on the file. So it'll show up at a few points. It kind of stands out a bit for that reason. But yeah. So in any case though, so we can maybe say, okay, let's see. So what we can do. Let's maybe for each logogram. Well, okay, there's a function called nearest neighbor graph that we could try. I'm just thinking of the best way we go about this. Okay, so there are a number of things we can do. So the first thing we can do is for each logogram, let's find the nearest to it and then get the image difference. So let's try that. So let's start with just the first 5 in I2, and we'll say we're going to find the nearest function of that logogram. We're going to find the 2 nearest, right? And then we're going to find the second of those, because again, the first nearest will always be itself because all those images are in the data set. So we want to get the second nearest. And then we're going to say image difference of that with the original. And so this will apply for the first 5. Okay, there we go. So this first one looks by far the most convincing. A lot of these other ones look kind of stupid. But okay, let's try it for maybe the first 15. Wait for it to run. Okay, so yeah, again, so that one looks potentially okay, but most of these look pretty silly actually. That one, I think that's the one we got earlier, or something like one of these. But yeah. So actually, okay, one thing I'm interested by is the fact that these two weren't paired up, if that makes sense. So for instance, the nearest to this one is this one, but I believe the nearest to this one is going to be, yeah, this one for some reason, which I don't understand because these two seem a lot closer. So what, I mean, it's obviously possible for that to be the case, but I think it seems like it's a mistake. So you know what, let's write our own distance function. Our distance function is going to be, actually I saw there was a function called this, and I don't know what this function does. Oh, no, okay, this does something totally different, but it's actually quite a neat thing. Oh, this is a new function, okay. So I'm getting a bit sidetracked. Right, okay. In any case, though, well, that's actually quite cool. Okay, well, this is getting sidetracked with image displacements. There's a function, okay, so we have image distance. So it's got these different method specifications. So let's see. So right, so this is getting the Euclidean distance. This is a very random thing it's doing here. It's getting the Euclidean distance of, I guess, just the pixel values. So what we can do instead, let's say we just want to get the closest by which have the fewest different pixels. So what we can do, our distance function will just be, so this distance function is just giving a thing a #1 and #2. So we can say we want to get image difference of #1 and #2, and then given that difference, we want the difference to be as dark as possible, because that means that they're the fewest. We want the average pixel to be very dark in that difference, because that means that they're very similar. So there's a function called image. Oh, crud, what's it called? It's called like image properties. It's like image. Image. Okay, let's look at component measurements is similar. So we can go to that one, and then maybe it'll be in the C alsos. Image measurements. Okay, yes, that's what it's called. So image measurements lets you just get a bunch of easy measurements of images, things like what's the maximum pixel value and so on. So I think we just want to get the mean or the total pixel value. All the images are the same resolution, so the mean and the total, the only difference would be just that one is multiplied by whatever the number of pixels is, so it doesn't really matter which we use, but we can use the mean. So essentially we just want to take the image measurements of that and get the mean, and that will be our distance measurement. So we can make this nearest function, and then, okay, and so now if we run this with our new nearest function, oh god, okay. Oh my god, that did not, that just exploded. Let's see what's going on here. Okay, so let's try something. Let's try setting this to, first of all, if I just say NF of this, does it work? No. Okay, well let's see what's going on here. So let's have it so it will print out these two images when it runs. Okay, that looks good. So those are those images. Now if I just take those images, I just want to see, okay, well, did this part work? Okay, let's see, did that part work? It appears not. Okay, let's see. So we can get that. We can get, actually that looks like it fed itself. Well, it fed itself the same image, but that's fine. So it's just doing some sort of like linear search by default, which is again what we'd expect it to do. But okay, hold on. Let's maybe just look at the documentation for nearest, so that we make sure that we understand distance function, the distance function option properly. So, right, okay, so that's getting the norm. That's what I would expect it to be. Actually, I wonder, does edit distance work with images? No, okay. Well, all right. Let's see. Method. Okay, that's a different thing. The methods here are something else. So let's see. Okay. Well, I'm just trying to see if there's anything relevant here. Okay, well, why don't we just do it like this? Let's see. I mean, we could write something trivially that does this ourselves, but I want to just I want to see what's going on here with nearest. So let's take this function here, and what happens if I just apply this to two of these images? If I say that of, and I give it that image, and I give it that image again, and get rid of the echoes, because it's not very useful. And I don't need that echo either. Okay, so it says 0. So it says that, oh. Oh, I see. Okay, right. So image measurements, for some reason, it's getting the mean of each channel. Is that what it's doing? Okay, hold on. How many channels do these images have? Because they're grayscale, or they should be, but they may have been saved as being RGB or something ridiculous. Yeah, they're saved as being RGB, which is crazy. So we'll fix that right now. I'm just going to say I2 equals, and then let's say, I believe it's called color convert I2, and I think I can just say grayscale. And there we are. And now if I take one of those, it'll look basically the same. If I say color separate, right, there's only color separate. It will look, yeah, right, it's just one channel. So we can maybe say just I2 equals that. Maybe not the best practice to save the variable over itself, but that should be fine. Okay, so now this should work. Because now image measurements return a single thing. We can maybe try running that again. So if I just say I2 part 1 and I2 part 1, let's just check if that returns it in the list. No, it does not. Okay, wonderful. So now if we create that nearest function, now if we run that, what is it? Oh, it's complaining about that. Okay, so it's complaining about that because that was an existing image from I2. But okay, so here we go. So okay, so this is looking actually a bit more convincing. So this first one, you can see it did really well, or it did the thing that we already did as humans, so that's a good sign. This next one, it looks again like the edges are a bit different, but it looks like it did find something that's very similar, except that this other one has the difference that it's got this little hook and it's got something going on down here. So that's actually pretty interesting. Or at least it seems to have done a good job there. Similarly for these two, it seems to have done a decent job as well. Again, we have these edges, so it's not perfectly lined up. Actually, okay, maybe, so a minute ago I got distracted by that function image displacement. So actually image displacement itself probably isn't the most relevant function, but there's a function called image align that probably is very relevant. Right, so the problem here is, if we look at, let me just delete that for a moment. If we go way back up, so the problem is, we've got these two images here. They look very similar. The only difference is that one of them has this little hook on it. And we just want to get the difference. And if I just say image difference of them, if we just get the raw difference between these two images without aligning them or doing anything like that, then the problem is that we get something like this, right? So you can see it's got the hook is different, but they're barely not aligned, and so the edges don't quite match up. So we can maybe use some sort of function to match up the edges automatically. So there's a function, I just gotta wait a second because I'm saving, and there are a lot of images in this file. So there's a function, first there's that function I was just looking at. So this is kind of a cool new function. So this is in version 11. So what this function is, essentially, it's basically an optic flow function. So given two images, it will try and compute basically what for each and every pixel, or I think for each and every pixel, how is that pixel kind of transformed, so to speak, from one image to the next. So for example, I'm pretty sure that's what it's doing. So for example, and it can look at transformations, or it could look at something like rotation. So we can see, for instance, like with these images of windmills. So it's got these images of windmills here. If you get the image displacement between these, where the windmills are kind of spinning, then it will find the parts that are spinning and so on. So that's kind of nice. Now there's a function that's kind of similar to this. Right, so these functions, this is a kind of older function that just does it for key points. There's a function that's similar to all of these, yeah, right here, this one, image align. And essentially what image align does is it essentially returns a version of image that is aligned with the reference image ref. So basically we have these two images, and they may be different. So for example, let's see if there's an example of a more complicated case. Right. So for instance, let's say we have this image here and this image here, and you can see that these images are they cover different places, but they do share a bit of stuff, and they're not identical. So they're not, this isn't just like cropped versions of the same image. You can see the waves are different, the clouds, the shading is different, and so on. And with image align, it will find out how to mesh them together, and so on. Or for example, with this picture of the Eiffel Tower, we've got a right side up one and a curvy one, and you can see it's got the curvy one with the clouds and everything in the background, right side up. So essentially what that means we can do, and let's see if this works. So I don't know how precise a function like image align is generally. So what we can do is we can say image align of that and this, and I believe that will align the second one to be oriented like the first one. Okay, so you can see it shifted it a tiny bit, which is why there's this kind of black border at the edge from where it shifted it. You can actually set for image align, I believe there's a function, yeah, you can set background. So here we probably want to say background goes to white, just so that we don't get that little black border at the side. So we want to get the image difference between the original image and the image aligned second image. Oh, there we go. That's beautiful. Okay, look at that. Look at that. So that is the actual, that's kind of the real differences between those two images there, and not just the literal pixel differences. So, whoops. So that's really what we want. Now, one thing to notice is that this is a lot more computationally expensive. So when I just ran that there, it took it a second. So if I say, let's try just saying absolute timing of that. Oh no, it's actually quite fast. Never mind. Okay, never mind. It seemed like it took it a second. It probably just took it a second because image align, depending on, right, so actually I doubt this is the case for image align, but there are lots of things. So for example, there are lots of functions that come in things called packlets, and when you first call them, it has to download a packlet just with some of the code in it, and then it will use it. And it's just useful for updates and things like that. But so oftentimes that's the case. If you run something the first time and it takes it a second, and then after that it's really, really fast, that's usually because it was downloading a packlet. But so I'm guessing it might have done something like that, but I'm not really sure. But okay, so in any case, though, this works really well. This is great. So let's just define a function that does this. So I don't know what we can call it. We can maybe just call it like aligned difference. And it's just going to take two images and image 2, and it's going to return image difference of image 1, comma, image align of image 1 and image 2, where they're being aligned with the background set to white. So okay, and now if I just say aligned difference of these two, aligned difference of this and this, then there we are. Cool. So now we can do a number of things. So the first thing we can do is we can go back to our nearest function. Oh, so actually, there's a bunch of stuff we can do. Okay, so the first thing we can do is we can go back to our nearest function and define it using our aligned difference instead of image difference. And so if we run that, okay, now if we get the nearest images, let me see where. Okay, I think I deleted the part that did that. That was kind of stupid. But let's say, okay, for each, let me just delete some of this, clean up the notebook a bit, and maybe we should define this a bit higher. So it's, if we ever run through this again, then we'll want it there. But okay, so what we can do, right? So we have this function here. Right, so we can say aligned difference. So now what this would do is it'll show us what's the difference between each thing and its each logogram and its nearest aligned thing. This is obviously being much slower because image align is slower. Oh, what is that? That's some sort of horrible thing. Well, let's see. So it's running right now. Actually, you know, I'm gonna stop it. I'm gonna run it for just. Well, okay, let's try this. If I just say random choice of I2, comma random choice of I2. Okay, there it is. There's the random difference between two of them. The question I have is just what is the repeated timing of this? So how long does it take on average? Given two random images, how long does it take on average? Okay, it says about 0.6 seconds, or 0.8 seconds, or I don't know what this compiled function error is. Okay, it's taking it like half a second or so, or it's being kind of inconsistent how long it's taking. And of course, right, yeah, okay, right. Of course, sometimes you can see, like in that case, in this case here, it looks like something crazy is happening, and that the answer is that the logograms were different enough that it couldn't really align them in any sensible way, and so they get aligned in some crazy way. And so, right, but in any case, though, so okay, so we've got our, actually, you know, well, right. So, actually, I'm curious how long this is taking to run, because I want to be able to estimate it. So first we can try doing that. So that's running repeated time. It's going to run it for 10 seconds until it's done, and then it's going to say how many times could it run it in 10 seconds. The other thing we can do is we can say, okay, that says half a second. I'm curious though, just for fun, just for entertainment, if I say absolute timing of that, and we get part 1, so that's the amount of time it took to run that. If I say table of that, comma 10, right, or let's say, okay, so if it's 10, that means it'll take about 5 seconds. So if I set it to, what's a reasonable number? What's a number we're like? If I do it for 30, we'll have to wait for 15 seconds. I'm just doing this so that I can say histogram of that. So okay, so we'll have to wait for 15 seconds. So yes. So we're waiting. Okay, that's not a very useful distribution or a very useful histogram. We don't really have enough data to do it. But okay, in any case though, so it takes about half a second. So given that we have 32 logograms, that means if it's doing, when you define a custom distance function like this, it has to do a linear search. So that means, let's think about what that means. That means that if there are 32 logograms, it means that it'll take about 15 seconds to search each logogram. So that's a while. So we can try running this, instead for the first 15, let's try just running it for the second. Let's try just running it for the second logogram and see what we get. Because it'll take about 15 seconds to do it. So we don't want to run 15 of them, because then we will be waiting for a while. Or I guess we'll be waiting for 15 squared seconds, which is longer than I want to wait for. Okay though, so that did a good job though. So we can see we've got the hook, we've got this little thing here. It seems like it has, and we've got this stupid whereas Abbott text. But okay, so that has actually, you know, extracted the proper things and everything like that. So that's nice. And again, if we, well, right. So okay, again, I'd love to make like a nearest graph of this, where for each one we find like maybe the 3 or 4 nearest, and then make a graph of each one with its nearest, with its most similar ones. But I think that's going to be too computationally expensive, or it's going to just take too long, you know, to do right now. I mean, I could certainly run it, you know, overnight, or it'll probably take like an hour or so. Or actually, okay, we can compute it. It's 15 squared. It's 225 seconds times 32 logograms. It's that many seconds, which is that many minutes. That's not that many minutes. It's 120 minutes. It's 2 hours. It'll take it 2 hours to do it, but I don't want to spend 2 hours in the middle of this thing here doing that. So best to wait on that a bit. So okay, in any case though, we can maybe just write here. Whoops. will take about 2 hours. Maybe on Chris's computer. So right. So okay, in any case though. So okay. So that seems reasonable. But now let's see. Let's see if we can. Okay, we might be able to optimize this a good deal by taking advantage of. Well, we could do a few things. So one thing we could do. Okay, we could do a bunch of things. The first thing we could try and do is when comparing them, when getting the difference between them, or when getting the distance between them, we could run image resize. So we could compare not the actual full resolution images, but some smaller version that we can compare much faster. Actually, speaking of which, how big are these? Okay, they're 500 by 500. So right, so we could image size them down to, I don't know, 250 by 250 or 100 by 100 even, and use those to compare, and it would probably be a pretty good approximation because I doubt we need all these pixels. Now that does make it a lot harder for image align, because I think image align does something like, I think it might use image corresponding points or something like that, which uses image key points, which cares a decent amount about resolution apart from just how many pixels are on the screen. Right? I guess that doesn't make any sense. It cares about. I think it cares about resolution because it cares about detail. So we probably can't just size it down like that. But now instead of that, though, we can still get these images like this that show the aligned difference. But we can find what's similar by using the feature vectors. I think that might be a good way to do it. So, okay, so let's see. So I'm thinking about just what the best architecture for this is. So we have our feature extractor. It's called Thef. So this is our feature extractor. And again, we actually still haven't tried the other method for this feature extractor. So, okay, to go on a tangent, we did the default feature extractor, but we still haven't done image, what was it called? Okay, feature extraction. There was, oh Jesus, okay, where's the, I just want to find, oh wait, feature new. This is a new function, new in 11 point. Okay, so this isn't out yet. This function is not out yet. So actually, I guess I was wrong. So I thought that nearest automatically might sometimes in newer versions use feature extraction, but I'm going to guess that you actually just use feature nearest instead of nearest. But again, so this function does not exist yet. So I guess I'll use it just because it's a bit quicker. But yeah. So I guess also right. I'm just looking to see if I think it works exactly the same way as nearest. So that's nice. So right, so I think we can just replace that with nearest. Now actually let me just check one thing quickly. So we can say, okay, right, so when I go to feature extractor, okay, hold on, there are a number of different things here. Okay, there's feature types. Oh man, okay, there are all sorts of different options we've got here. Okay, let's see. So first, before we get to feature nearest, let's just look. Feature extraction you can give it these different extractors or extractor methods. So we can try maybe using something like image features, which might do something different from what it does by default. So let's try, if I just do that, let's see if we get a different answer. So it's running, it's training, okay. Let's just see if this is the same. Property image is not, oh, yeah, that's not right. So we'll just see if this looks exactly the same. It looks exactly the same, but it's flipped. Okay, so these are essentially, it basically doesn't matter if we say image features. It already figured out what to do. It's already using the right thing by default. Oh, or not. Oh, so it's different now that they're grayscale. Because remember, we made them grayscale since we've done this. Okay, that is interesting. I'm surprised that it cares if it's grayscale or not. I'm really surprised that it cares. But it's not necessarily wrong, but it's just that all the channels were the same, so I'd be amazed if it got really much. But these seem to be reasonable anyway. I mean, those look good, those look okay, those look fine. You know, this group looks okay, you know, and so on. So this isn't necessarily bad, yet those look good, and so on. So let's see though. So we'll use feature nearest in just a second. Let's maybe make that a bit smaller. Okay. So right. So I guess actually it does matter if we use that option that said, what was it, image vectors, I think. So I'm gonna write both versions here. Write the one that we're not currently using above. What was it called? It was called image features. Okay. It's okay. So now we have these two versions. It's not totally clear which one is better. So we can sort of try both and see what we get. But okay, so let's just do this. So we've got this. This is nice. Let's say feature nearest. Again, the function that doesn't exist yet. So we'll say fnf for feature nearest function, because we've already used nf for nearest function. And what do we give nearest function? We said, where do we create a nearest function? Okay, we just gave it I2. That's all we did. Just give it I2. So we'll say feature nearest of I2, and that's it. Okay, so now let's say fnf of I2 part 1. Okay, that'll give us itself. Okay, that worked though. So this is what we were doing again before, but instead of using nearest, we're now using right. So okay, so we can literally just run the same exact thing. Right, so this is using the nearest function, just change one character, now it's using feature nearest, except that doesn't look nearly as good. So that picked, so again, it's getting a good result for the first one, but it's not getting a very good result for the next one, or that one is not as good. Yeah. Some of these, again, these crazy distortions here, that's because image align presumably aligned them in some crazy way, and distorted them and trying to align. Okay, but like that one, it did a good job. Okay, number 7, it did a good job. I wish it did a good job on more of them, although it might just be that some of them just don't have, some of them might just not have super similar logograms. Oops, sorry about that. And so some of them might just, right now we're not really giving it the option to kind of cop out and say that none of them are similar. So it's always going to do something, and so when it does something silly, it's maybe not necessarily that surprising. So okay, so let's see though. We can try running this for a bunch of them. So how long did this take to run, first of all? So how long does this feature nearest take to run? Let's just check it. I say random choice just in case a function like this might try and do some clever caching or something. Okay, so it's 0.011 seconds. And again, actually, we still haven't tried using the other method option for this. So again, right now we're using the default feature extractor, but we could always use that feature extractor called image features and see if we get a different result. Okay, so let's see. So we've got these here. So let's try. Okay, staying with this. We'll just say maybe compute this for. Okay, first we could try just computing this for the first, say, 10, and that should be fast. Whoops. Okay, why is that only returning? Why is that only returning 2? Okay, hold on. Let me think about that. Oh, of course. Yeah, there we go. So, right. So that is going to be pretty, that's going to be plenty fast. So now what we want to do for each of these, right. Now actually, thinking there's another way we could do this actually. I think the feature vector way is probably better. And honestly, you know what? No, this is exactly how this would work. Right. No, never mind. I was going to say what we could do. Instead of using a feature vector and then finding the nearest things with the feature vector, we could try using classify and say, okay, give us the two closest logograms using this classifier to a particular logogram. But if we did that, we'd want to set it to use a feature extractor, and I'm almost certain that it would end up picking, it has different methods for different things. I'm almost certain it would end up picking nearest neighbors as a method, and so it would be exactly equivalent to this. So there's no point in doing that, really. Or there probably isn't a point. And honestly, this will probably do pretty well. So, okay, in any case, though, right, we can try running this for a few of these. So again, it'll take about 0.5 seconds times the number that we're doing. So if we're doing 15, it'll take it like, what, 7.5 seconds. So this would take just a few seconds. So we're waiting. Again, I don't know what that error is there, that message. Okay, so again, a bunch of these are silly. These ones are not silly. Those ones look very good. That one is silly. These ones are kind of silly. That one's okay, but it's a bit silly. Okay, let's maybe try the next. Let's try like the next 15. You know what? Let's just do all of them because it doesn't take that long. It's taking about 16 seconds to do all of them. So it's not that. It's not that long. We can be a little patient. So okay. Again, I don't know what this compiled function error is. Okay. So the first one looks good. These ones are pretty good. Oh, that one looks interesting, potentially. Yeah, that one, those ones look very interesting. That one looks good. That one looks interesting. That one looks good. Okay, so actually there are a bunch of these that look pretty darn good. Yeah, okay, this is not looking bad. So, and that one looks good. That one looks really good. So, yeah, okay, cool. So let's see here. Let's see, I mean, we can kind of rate these a bit by just saying, well, okay, right. So there are a few ways we could do this. The first thing we can do, okay, right. So the first thing we can do is we can just have an, well, okay, so I guess, okay, we've already accomplished most of kind of the goal that we set out to do, which was to try and see, okay, are there parts of these that a lot of them have in common and so on, and are there bits that are maybe like shared, and we've definitely seen that. So for instance, if we look at this image here, we can see that there are two logograms, and this looks to be kind of a unit that was added to an existing logogram, which maybe would tell us that this is made in Photoshop, or maybe and maybe would tell us that you know, that this is how the alien language works. It would probably tell us one of the two. But if we're trying to be kind of in character, then we wouldn't do, then we'd probably not assume that the aliens made their logograms in Photoshop. And so we've got also, you know, these ones look good. So again, we can see it. There's some existing symbol, and stuff was added to it. So actually, even okay, right. So this is again the annoying symbol that just has, for some reason, somebody wrote "Where's Abbott" on it, which is, I assume, the translation. Or which I believe is the translation of this. So again, okay, so that's actually kind of cool though, because if we look at right, so if we look at something like this, I believe either this or this is the sign for Abbott, if I remember right. I'm not entirely sure because this is a while ago, but I'm pretty sure one of the two of these was the logogram for Abbott. Oops. And so basically, looking at this, right? So we can guess maybe you can see how this was made. Basically, we can see that they took the sign for Abbott and they added these little thingies. And so, right, and I know, and I think this is even mentioned in the movie where someone says that, oh, it's a question, and so it looks like all the questions have this little hook on them. And so I think that's what this little hook was meant to be, because this is a question, of course. And then I guess this blob they've decided means where, or where is, or something like that. And again, this has not been, I don't think that there's really, anyone has actually really sat down and made kind of a proper language out of this, but it was more just they were kind of, this blob seems to mean where, this blob seems to mean Abbott, and so if we want to say where is Abbott, we just sort of somewhat randomly combine those blobs together to make something that kind of looks like both of them. But we can see how that was done, and so we can see that we can see what's in common and we can see what's changed and so on. So that's kind of interesting. And now now that we have that, we can maybe even do something where we find, say, all of the logograms that have this blob on them, right? So we could say, I'm thinking about exactly how we might do that. Well, okay, I mean, yeah. So, well, okay, we maybe come back to that a bit later. But yeah, so I think that actually did a fairly good job of doing our kind of stated goal. Let's see, what can we do now? So we can look at these for a minute though, because it actually did decently on a lot of them. I mean, again, there are a lot of these that it kind of failed at, which are not super surprising because they don't look all that similar. Like these two, right, where it aligned them in some silly way. But again, it doesn't really surprise me terribly much because they don't look all that similar. And so there probably just isn't one that's super similar to this one. But right. Actually, what's this one here? So if we say that's what? That's number 12. So if I say I2 part 12. Okay, so that's another good one. So you can see this one here. So we can see this one here. So if I say FNF of I2 part 12, this one, it did very nicely. Right. So it found that there was that both of these logograms exist, right, which are very similar, but where the only difference is essentially this little area down here, I guess, and I guess just something going around like that. So there's the difference between, oh, and then also the little hook that we see again from up here. So so right, and actually it looks like it's even just very slightly different hook because it doesn't have this little twiddle. Actually, that little twiddle there is probably just because something was, yeah, it's just because this blob goes like that. Right, okay, in any case though, yeah, so we can see we can actually do some fairly sensible things with that. But okay. And I mean, I guess the point about this is just that it's kind of neat because this is using, I mean, there's some fairly fancy stuff going into this working. I mean, we're doing, I mean, just to recap sort of what's happening here. We are first, and why don't I go up so we can go through the code. So first, we're creating a feature extractor that is using whatever it's using, perhaps some sort of neural network, who knows, but it might be using some sort of neural network. I think that the general feature extractor things generally, okay, no, this is just saying oh no, never mind, that's the feature space distance, right? So it's getting some 37 dimensional vector that it's extracting from each of these images by some means that may involve machine learning in some way. And then it's creating a nearest function. So in this case, it'll probably default to a k-dimensional tree to search with them. It's then when we give it a logogram to find ones that are similar, it's then running the feature extractor on the inputted one, finding the nearest thing in Euclidean space in that with that k-dimensional tree, and then we are using image align, which is using various key point things, I think, to align the two images, and then we're taking the difference and we're looking at the difference, and we're actually getting reasonable results. So there's a fair amount that's happening kind of behind the scenes there, which is kind of neat. Now, one thing we can do here actually that I just realized, we can set this to use a different feature extractor. So right, so I think we can say feature extractor arrow image features, and that will use the other method because we know that those are actually slightly different. So we can just see this might work better, it might work worse, who knows. That looks dramatically worse. But let's see what happens when we run it for all of them. I mean, again, it'll probably vary a bit by case, which does better and which does worse, and so on. So we'll see. But yeah, again, we still haven't run. We could still do the aligned difference for every for all of them. Basically, we get all the pairings except again, that'll take about 2 hours, so I'm not going to do that right now. Okay, so these first two did pretty well. Let's see. That one looks pretty good. That one does not look good. That one does not look good. That one looks okay. Those ones are good. Okay, those ones are new. Let's copy one of those down. So we can maybe just like collect some of them that look good. Let's see, did it get that one? Okay, it didn't do that one very well. Yeah, although that looks like it might have been image align that was at fault there. But okay. And then let's just see. Okay, so let's go back. Let's do the version that used the default feature extractor because that did seem to work a bit better. So we'll leave it with that just so that we've got the better version running in the notebook. But okay. Just let that run for a minute. Just take about 7 seconds or so. Okay, there we go. So okay, so that's all well and good. Let's see, what other things could we do? I'm gonna save this actually. So let's think about what other nice stuff could we do. So we could try a few other obvious things. I don't know if I should create a new, I kind of want to create a new notebook because it's starting to take it a few seconds to save that one because it's so full of images. So it might be good to just make another notebook. Right, so we can try maybe doing some other things. I mean, there's some other obvious things. So an example of one obvious thing would be to just say image difference. Let's see if there's something common to all of the images. Right, so first of all, we can try saying image difference. Oh, okay, image difference only takes 2 arguments. Oh, that makes sense because it's like XOR. Yeah. So we don't want to do that. We want to say, I don't know. I'm thinking about what the best way to write this is. Well, okay, we could say image subtract. Right, so we say image subtract of all of them. So this would be the same as image adding. Oh, that's not. Okay. Okay, let me just think about why that did not work the way it might have. I'm just thinking about if we want to color negate them or something. If I say image add, I'm just thinking about exactly what we're doing here. Okay, so given that we have 2 of these, I basically just want to see what's in common to all of them and so on in a kind of trivial way. So let's see. So if we add, I'm just thinking about, because basically it's sort of unintuitive because they're the kind of quote, when you're running something like image add, what's considered to be the kind of quotes negative space is the black part, the part that we think about as being part of the logogram, and so it's kind of it's kind of unintuitive. Just because the logograms are black on white instead of white on black. But okay, but so let's see. So if we what's the right function? If we say right, so if I run image if I run image add of that, actually we can run image multiply of that, and what happens if I do this, right? So this will say right, so that basically combines them, I believe. Yes, right, that's what we want. We want image multiply. That combines them, essentially. Right, yes, I'm just looking how these are not quite aligned as I might have thought they would be, but okay. So, okay, that's right. That's all we need to do. So we can just say image multiply of all of them. Okay, so there they are all on top of each other, complete with the one that says where is Abbott. Okay, it's just kind of amusing, and we can see that the little hooks wherever they appear, on the inside at least. Yeah, we can see sort of the general width. There's a bunch of like random statistics that we could probably do. Like for instance, we could probably say something like color negate / at I2. So there they all are. And then if we said image measurements of that comma mean, right? So this would give us the average. What's the average pixel value? So basically, how much of the image, and because we color negated it, it's basically saying for each of these, how much of the image is black and how much is white. And so we can maybe look at the distribution of those and get a sense for, are these on average more, like, are they lighter or are they darker and so on. Okay, so they're on average, I guess, that dark. I mean, that's not super useful, but maybe the distribution. I mean, the problem is there are only 32 things, so the distribution isn't super useful. Let's maybe set it to something like that. Yeah, that's not the most useful histogram in the world. I'm going to put this back in the original file because I don't think we're going to forget it there. But okay, so that's fine. Let's maybe see though. Okay, let's change course a bit. So we can do, let's see. So, okay, one of the other things, I think I'm gonna want to wrap up around maybe 10 or so in my time zone, so in about maybe 20 minutes or so. But so before then, there's maybe one or two other things that they haven't covered yet. So one of the things, yeah, this doesn't necessarily have to do terribly much with the logograms, but it was kind of an interesting, fun thing, and it might be fun to look at a bit. So one of the things is that, well, okay, I don't want to spoil the movie, but there is a scene in the movie where there's a scene in the movie that sort of earlier on in the production seemed like it was going to be more prominent than it ended up being. But so the basically near the end, and again I'm gonna try and avoid. I'm thinking about how to say this. Near the end, there is a scene of the movie where the aliens kind of they sort of show like a ton of logograms very quickly. So they just sort of show like thousands of logograms really quickly, and there were different ideas about how they could be displayed and so on. And so one of the things, just kind of for fun, is we were looking at having them grow with a two-dimensional cellular automata rule. So I don't know how many people in here know what cellular automatas or cellular automata are, but I can maybe just, well, let's see. So essentially the idea is that there'd be the idea for how this might work is that there would be just a single logogram like this one. I think actually this is the one I was playing with, just sort of sitting in the middle, and then you'd run some two-dimensional cellular automata rule on this logogram and then see how it evolved. So an example of one of those. So basically, let me see. So there's a function in Mathematica, or sorry, in the Wolfram language called cellular automaton, which lets you just run cellular automata, and it lets you do all the general stuff. So you can run, and actually this is a new function. I haven't gotten the chance to play around much with it yet. But okay, but it lets you run cellular automata in very general ways. So you can run two-dimensional ones, you can run 8-dimensional ones, you can run 8-dimensional, 2-color, outer totalistic, cellular, you can do whatever you want. And so we can try it. Okay, I have long been opposed. This is a very old function. I believe this is a version, it's not actually that old, it's a version 4.2 function. But the rule specifications are incredibly complicated. It is because it's very general, but these rule specifications never made much sense to me. Like the design of them seems kind of random, but they end up just looking like these weird collections of random lists and numbers and so on. So I'm not a particular fan of the design of this function, but we can use it here because it's nice and it's very fast and everything. So okay, so the idea here is we can try and maybe just say, okay, let's take this and let's just run some rule on it. So let's see. So we can try. Okay, let's just steal an example and try using that. So this is, let's see what this is doing. So this is running, and we'll put we'll say maybe array plot of that. So this is running. It's okay. Given, so the way the cellular automata function works, the first argument is the rule spec. So this is specifying the rule. This is the initial state spec. So that's specifying the initial state, and this is specifying what we want to get back. So basically, this is specifying we want rule number 14. And then these things, I believe this is the neighborhood. So the point is you can have cellular automata that have higher, like larger neighborhoods and so on. So I think this is specifying the neighborhood, although I'm not totally sure. And then this I think is vaguely, or no, sorry, this I think is specifying the radius of the. Okay, let's just look at the documentation. Okay, so it seems that, right, so we've got the rule, and then we've got k. Okay, so the 2 is the number of colors, so it's 2 colors. The 1 I think is the, okay, then the r is the range. So this list 1 here is, I guess, it being totalistic. Can I just say 1? No, okay. I think that just means it's totalistic. In any case, this thing works. So we can try taking this. So given that we have I, let's just take I, which is just our random logogram. So we can say, first of all, we can say imagery size, and maybe make it, I don't know, 50 pixels across. Just make it really small so we can do stuff with it. And then we can binarize it. So okay, so there's just a very small kind of logogram that we can maybe play around a bit with. So instead of using this as the initial state, we're actually going to use this as the initial state. Now, if I say image data of this to get the array, 1 represents, actually you can see, I don't know if you can see this on your computers, but this is laid out so that it's like doing an ASCII art thing where the zeros are shaping the logogram. But basically, basically though, with cellular automata, well, right, for this particular rule, let's just as convention, because when we're using array plot, this is how it works and so on. 1 is thought of as like the cell being white, and 0 is thought of as the cell being black. So we want to actually run color negate before we get the image data, so that the logogram is white. But okay, so in a sense, it doesn't actually matter, because you can always get the cellular automata rule that's like the complement of it. That's like the complement of another rule, and then it doesn't matter. You'll just invert the colors. But whatever. So I believe we can just set that to be the initial spec. Okay, that was very random what it did there. I think we can do this. So what that did is it padded it with zeros. So what is this ridiculous mess that we're looking at here on the screen? So I think we can do this. let's write this. So basically what this is doing, and I don't want to say list point, I want to say list animate. So what this is doing, I'm going to let it run. Oh, okay, wait. This is a bit of a spoilers, or spoilers for the code, not for the movie. But basically what this is doing is it's running the cellular automata. It is using this rule specification, but instead of starting with a single cell, it's starting with this as its initial state, or it's actually, I guess, starting with this as its initial state, and then it's going to pad that with zeros if it grows out of bounds, and it's going to run it for 30 steps, and then we're going to animate that. And so if we do that, we get this, this nice pattern. It's not a particularly nice pattern, but this is just the first rule we tried. So the whole point here is that there are lots of rules. So here we're just using totalistic rules, but we could use a larger space of rules, and we can just check, hundreds of thousands of rules, and eventually we might find one that does something good. So let's see here. So I think we even have, I just want to see, so here, I want to just see what the rule specification we're using here is. Okay, generate frames. So this is the rule. Okay, so this is the rule specification we're using. I'm just stealing that. Okay, that's the code that was actually used when working on the movie, but we're sort of recreating some of that. So this is the code that was actually used. So let's say rule 14 of that in this space. So this is a totally different space. Okay, so that does something totally different. So let's try and, okay, let me go back here. Just for the sake of discovery, okay, let's pick a rule that I know is kind of interesting. So we'll pick maybe this rule, and let's run it for, okay, we'll do it for 30 steps again. Okay, that didn't get very far, but it's still doing something kind of cool. Let's run it for 1,500 steps, and hope that there are various ways that this is not being as efficient as it might be, like using array plot instead of image and things like that. So hopefully this is not going to take it too long, but yeah. So hopefully it doesn't take too long, but because it's not really the optimized version, but it should be fine. Okay, let me actually, I'm going to stop this. It's being difficult about aborting. Okay, I'm just going to run quit. Okay, so because I quit the kernel, I'm going to have to reload the images. So the images, I believe we got those from the file. I think we got it from, yeah, I think we load it. Yeah, we load them right here. We only actually need, right now, well, we might as well get all of them. So right now it's just loading all the logograms from memory, or from the disk. Okay, there, it's done. So, okay, let's not run that for 50. Let's run that for 100 steps. Let's see what we get. Okay, that's kind of cool. That's kind of neat. So we can see, we're getting some nice patterns. So again, this is just trying to be kind of a visual thing for the movie. So this wasn't for a background screen. This was just supposed to be just playing around with different stuff. But okay, so that's kind of neat. And again, this rule was found just by trying thousands of rules. And so actually, I think we even have the code here. So let's take a look at the code that got that rule. I believe this is the code that got it. So essentially, what this was doing, right. So what this is doing is it was generating all sorts of, it was just trying a bunch of random rules, and you can see here it's just picking these random rules, and it was generating basically that animation for all these different rules for 100 steps. Once it did that, then it would check, it would basically check, so essentially the first criteria for it being kind of interesting in this particular case is we want it to be so-called slow growing. We wanted it to kind of spread slowly and not super fast, because there are lots of these cellular automata that grow basically at the fastest possible speed, which is one cell per step in each direction. But basically that's it's not going to have some interesting border shape if it does that. So we basically want to find something that grows very slowly. And so basically all this is doing to select them is after it's computed these right here, it's going to, so we can actually just run this, although hopefully it doesn't take too long. So we're going to just generate, oh geez, okay, hold on. What is going on here? Okay, hold on just a second. Generate frames. Conjugate binarize image data. Okay, does this not work in some sensible way? And the size 100. Okay, let's just see what's going wrong here. The image pad is being difficult here. The problem is that there's some color space thing. Okay, well we don't need to run this now, but basically what it's doing, okay, I can just say color convert. There are two things I can do. First of all, with black, I think I can just say 0 instead of black. Maybe let's just try it. So do something like that. Can I say 0? Yes, I can. Okay, so I can just say 0 there and it'll work. Right, so again, if I run this is just some random example. Right, that does some whatever interesting thing. You can see that grows slowly, and that's a nice rule there, and it looks visually nice and so on. So okay, so if I run this, what this is doing is it is getting, I think, 16 different rules, I think. So once we get those, okay, so now we can look at all those rules simultaneously. So basically, this is getting just 16 totally random rules, and it's got the rule number, and then it's got the animation of that rule. And so these rules might do whatever they do. And so we've got a bunch. So I don't know. I can zoom in a bit here. So we've got these ones here that sort of form these diamond shapes. These ones that form the squares. We've got this one, this one here, which just sort of stays in one place, which is kind of nice. Except it kind of turns into white noise. We've got this one here, which has got these cool kind of maze-looking patterns, and so on. So there are lots of rules here. But so we can just generate. So again, this is just generating them in groups of 16. But basically, we can just generate, for instance, if we really wanted to look, we would generate like a few hundred of these, and then we would just select all of them that meet certain criteria. So in this case, we're just looking for some easy criteria, like that it doesn't grow very fast. So after all of its steps, the criteria is just that it's got it's got fewer than a certain number of pixels. And so if we do that and we can find some good rules, then we can find some nice cellular automata that are pretty nice looking. So these were a few that we found. So we can take a look. So let's see here. So first we've got some pictures. So that's kind of a nice one. And again, I think these were all growing. Actually, I'm not sure. Some of these might have been growing from a single pixel, and some of them might have been going from, I think these images here were growing from a single pixel and not from a logogram. But these were basically just a selection of rules that grew kind of slowly. And you can see these, I mean, like these ones have like particles of some kind in them. So they've got these little parallel things going on at different angles and so on. That's got these little lines and so on. And so we can keep looking. Now, here's an example of one of the really nice ones, though, in my opinion. So this one, actually, I can open it like this. So this one here, so this is growing from a logogram, but you can see it's got all sorts of nice intricate detail, and it's got these nice sort of offshoots that look kind of neat and so on. And it's just I think it looks nice. It's a nice kind of very complicated pattern. Now there's actually, that's not the right version. There are actually animations for some of these. So the point is you can animate them growing. So for example, if I can open this up. So we can watch this actually growing. So this is, I think, running at like 30 steps per second or something, but I can speed it up. But I think that's it's kind of a cool. I don't know what the frame rate looks like on the other end here actually. So, but it looks very nice for me. So, and then we can try and watch that. We can watch that a bit faster. And it kind of has this nice pattern. It kind of looks like ink. Ink kind of spreading on paper or something. But right. So, okay, so that was like one of them that we found. And then there's some other good ones. So for instance, there's this one, which is another one that kind of looks like ink spreading, but which has these nice kind of offshoots at right angles. But yeah, and we can watch this one too. So yeah, so there were lots of kind of nice rules that we found for these things that made these kind of visually nice growing structures. But in the end, none of the cellular automata here made it in, I don't think. Or made it in any way that I could notice. So in the end, they didn't make it, but I think they were kind of neat. And we found some other ones that weren't quite as exciting. Like, I don't know, we can look at this one. This is not exported correctly. Let's see, is this one exported correctly? No, okay, that one is not either. So, okay, in any case, though, so right. And then we also tried to get some, right, so one of the things that we tried to get, so all of these examples of cellular automata, these were all running on a square grid. So that is the pixels are on a square grid. But you can also, you can do cellular automata that are not on a square grid, that are on some other grid. And so we were getting cellular automata on a hexagonal grid, which might make some nice patterns that had things kind of like more circular looking patterns. But in the end, I don't think we didn't get super far with that. I don't think we ended up finding any really good hexagonal rules. Other than, actually, I think that might have been these. I think what these were, these were hexagonal. I'm not entirely sure about that. I'm trying to remember, but I'm pretty sure that these here might have been rules on a hexagonal grid, which explains why some of them have these kind of weird angles. And if we zoom in, they're drawn as squares, but the point is that you can draw them so that, yeah, this is on a hexagonal grid. Yeah, you can see, because if you, let's see if I can open this so that I can zoom really far. You can see it's a hexagonal grid, because if you look, yeah, it's on a hexagonal grid, because if you look, look at like this right here. So those aren't actually pixels, those are just, the pixels you can see are much smaller. And so this is just a quick way of approximating hexagonal grid and rendering it in a way that will take reasonable time. So yeah, so this is from a hexagonal rule. Now, of course, you have to do a bit to convert the logogram to be to sit in a hexagonal grid, because it doesn't by itself. But that's not too bad. So yeah. So all right. So I guess just we should probably wrap up in a minute here, but I guess we can go through some of the things that we did here. So the main things that we were looking at how we were trying to see if we could find similarities between different logograms, or different, again, logograms, the term that they used in the script, although I don't think they used it in the final movie, for the different symbols from the aliens. And so essentially what we were looking at is we were trying to find different logograms that looked similar and that might have meant similar things, or that might have certain key differences that might tell you something about their meaning and so on. And so again, sort of from the perspective, imagining as if we were a character in the movie, what might we do to try and investigate this? And so we ended up, you can do some amount of just running image difference, but the things aren't perfectly aligned. and so we wrote something that used a function called image_align that itself internally, I think, looks for image key points and things like that to try and align the images. And then once you do that and compare them, it does a really pretty good job. And then once we had that, we could use feature extraction and a function called feature nearest to use some kind of machine learning methods to find logograms that were kind of visually similar. And then given those, we can check the differences given that we can basically compare the feature vectors for logograms much more efficiently than we can get our aligned difference. And so it means that we can easily find, without having to wait for the approximate 2 hours that we'd have to wait otherwise, we can try and find these similar logograms pretty quickly. And then once we find those, we can look at the differences. And once we do that, there are lots of nice components that just sort of pop out, like this or like these and so on. And then the other things we can do is we looked at okay, once we get the features extracted, we can do dimension reduction and make a chart like this that sort of shows theoretically kind of conceptually similar logograms. Like these ones are all pretty similar, and so they're in the same area. In here, they're all kind of clustered together, so it's hard to see. These ones are kind of similar, and so they're close together, and so on. And we can make these clustering trees that sort of also show similarities. So you can see these ones are pretty similar, and these ones are relatively similar. Those ones are pretty similar, and so on. So they're close together. And then here's just another arrangement of that clustering tree on the same vectors, but using a different cluster to similarity function. Yeah, and then we just as the last thing, we looked at all of the logograms on top of each other. So that's like the union of all the logograms. We could also look at the difference, but whatever. In any case, though, actually, I think we could just now I'm getting a bit sidetracked. I was trying to wrap up for a second, but I think we can get the image difference just by saying something like that. Nope. Okay. Whatever. That's for a later time. But yeah. So there are a bunch of other things we could do, and that some other things that we looked into for the screens in the movie, but I don't think actually made it in the end. I mean, we can do things like there's like functions like image mesh, for instance. So we can look at the image mesh for say color negate of I, right? And we can so now we have this basically it vectorized it. So this is a vector now instead of a raster. And then we can do all sorts of fancy stuff. So we can find we can look at the geometry. We can do all sorts of fancy things. And then we could also do stuff like we can look at a morphological graph of I, right? So this, or I want to say color negative I. So this is this thing here. This is basically a graph. So this is not an image. This is just a graph that's been laid out conveniently to look kind of like the image, but that represents kind of connectivity in the image and so on. Or we could look at, for instance, a morphological graph of the thinning transform of that, right? Where the thinning transform will make it look all stringy like that, or we could say maybe the skeleton transform, which also makes it look kind of stringy. We can try the thinning transform, right? And there it is. That actually might be what it does by default. Actually, I think that is what it does by default. But in any case, right? So there's lots more that we could potentially do, and there's lots more that was actually done that didn't get around to seeing. But yeah. So I think I'm going to leave it at that. I'm probably going to try and make this notebook available, if possible, in some way, and people can play around with it. Although I should again note that some of the function that I think the feature nearest doesn't exist yet. So actually, I'm going to, before I finish, I'm just going to write right here. Feature nearest is only available in 11.1. Right. So in any case, though, I think that'll be the end of it there. So I guess thanks everyone for sticking around, and if you have any questions or anything, I'll probably stick around for a few minutes after this is over, or you can email me, and hopefully the notebook will be available. So thanks a lot, everybody.